right, let's go ahead and take a look at passage 3. Cloud cover is the percentage of Earth's surface covered by clouds. Cloud cover may increase because of an increase in the cosmic ray flux, the number of high energy particles from space reaching Earth per meter squared per hour. Table 1 shows how Earth's cover of low clouds, 0 kilometers to 3.2 kilometers altitude, varies with the cosmic ray flux. So like low clouds also include fog, I guess. Figures 1 through 3 show the relative cosmic ray flux, RCRF, the percentage below the flux measured on October 1st, 1965, and the monthly average cover of high clouds, 6 kilometers to 16 kilometers of altitude, middle clouds, 3.2 kilometers to 6 kilometers of altitude, and low clouds, respectively, from January 1980 to January 1995. Is it worth it to annotate? Like, you mean take notes as you take the test? I would probably like put a star here maybe. Like if I'm gonna annotate, I usually don't annotate, but if you ask me like to annotate the notes, I would probably like put a star here because I need to remember what the cosmic ray flux is. It's like kind of hard to tell the first time around what's going to be important, what's not going to be important. I mean, I would say just do whatever works for you, right? You try it, see if it works. You definitely, the more you practice, the better your skills are going to get. Definitely, if you find something really good, let me know, right? One of the things I really miss the pre-COVID era is like when I worked with kids in person. I would learn a lot of things myself because some kids would have some like really interesting techniques, and now I get to share those with you guys, right? So we have this table 1. So we have cosmic ray flux. What is that again? It's high energy particles from space. That's cool. So that's a lot of high energy particles coming from space. And then we have cloud percentages. So here, it definitely, the ACT, what do they want you to see, right? They just want you to see that like as low cloud cover percentage goes up, cosmic ray flux also goes up. Like this is the type of thing. Very common question type. They'll ask like, if the cover of low clouds was 27.9%, what would you expect the cosmic ray flux to be? And then they just want you to see like maybe 350,000, right, in between these two numbers. If the percentage is in between these two numbers, then the cloud ray flux should be between these two numbers. Another question that's very, very common, they might ask like, I'm like 100% expecting this question actually. They're gonna ask like, if the cloud cover of low clouds was 30%, what is the range of possible cosmic ray flux values? And then they're looking for like, 440 or 450. What do we have here? So here we have some funky graph. Figure 1. This is table 1. This is figure 1. January 1980 all the way to 1995. We have monthly average cover of clouds. Yeah, sure, that's the dotted line. And then we have the RCRF. What is RCRF? It's the relative cosmic ray flux. It's the so in table 1 they give us, let's talk about this a little bit, right? So we have the cosmic ray flux in terms of particles per meter squared per hour. So they're just measuring like meter squared is actually like pretty big. Like a meter is pretty long, right? Cubic meter, yeah, this is like the size of like it's a square, but it's like the size of like a decent television. Pretty big, pretty big. And then the relative, yeah, so like they're saying that in any given hour, if you have a square meter, right? Yeah, like this is like smaller than the car, yeah, about the size of a big screen TV. They're saying that in 1 hour, like over 300,000 particles will strike it, which is crazy to think about. And then what is this RCRF? This is the relative cosmic ray flux. So they're just calling the cosmic ray flux from October 1st, 1965 as 1. And then so anything under 1 is going to be less, and anything more than 1 is going to be more. No, that's not quite right. Why is the RCRF upside down? The percentage below. Okay, so it sounds like for whatever reason in October 1st, 1965, there was a ton of this cosmic ray flux. And then it's measured, yeah, the relative ray flux is measured as like a percentage below that 1965 radiation level. Yeah, so here, this would be 2% below. Over here we have like 7% below. It's not that complex. You don't need to think about this too deeply. I'm just like trying to explain it to anyone that's curious, right? And then we have, what's the difference between figure 1 and figure 2? Maybe these are just like two different locations. Like, I don't see any difference. Oh, so the only difference here is this one is high clouds, this one's middle clouds, and then this one is low clouds. That's actually very important. Yeah, this type of thing you absolutely need to know, right? Like, if you have three very similar figures, what is the differences between the figures? And then probably the thing that the ACT wants you to notice, and definitely, it's basically guaranteed that you're going to get questions about this, is that it seems like the RCRF depends on the low clouds, right? Because the graph of the RCRF matches the low clouds, not the other clouds. Okay. Question 13. The percentage of Earth's surface covered by high clouds in January 1987 was closest to which of the following? Okay, so high clouds, right? Which one's the high clouds? Over here, figure 1. We're looking for 1987, so this is 5, 6, 7. And then we're looking for the dotted line. And then this is another thing that the ACT does all the time. They overlap graphs, right? So there's two y-axes. Right side is RCRF. Left side is cloud coverage. So you definitely want the cloud coverage, right? So I guess we're January. Yes, January. It looks like 13.5, 13.4 maybe. Yeah, definitely B. Let's look at that one more time. This is 85, right? So it's 0, 1, 2, 3, 4, 5, 6, 7, right? This is definitely 1987. And then, yeah, if you just go across, let's zoom in, right? Maybe it's not super clear when it's so tiny. Mac, chill a second. So this is 87. You just, move your pencil across. It's 13.5 for sure. Okay, very simple, very simple. So here they asked you to definitely the high clouds, right? The important part was the high clouds. 1987. Based on table 1, cosmic ray flux of 440,000 particles per meter squared per hour would correspond to a cover of low clouds that is closest to which of the following? 440. Okay, yeah, okay, so it was actually the opposite of what I was thinking, right? So I was thinking they would say, 30%, what is the cosmic ray flux? They actually do the opposite. They tell you, imagine 440, what is the expected percentage? And here you need to recognize, it's going to be above 29, maybe 29.3. Yeah. So here, okay, so this is a really good thing to talk about, right? So, why not J? Why not J, though? Okay, great question. Why not J? How do I know it's 29.3 and not 29.6? Well, here, let's take a look. I mean, I don't know for sure, but the 2 points that I looked at is this one and this one, so I recognize that the percentage goes up by 0.3, and then the cosmic ray flux goes up by 20,000. So it's a very natural assumption that if it goes up another 3%, that it'll go up another 20,000. And definitely, this is the trend overall in the chart, right? So every time the percentage goes up by 0.3, the amount of particles goes up by 20,000. This chart definitely shows a linear growth. And I would say, in the science test and the ACT, it's almost always linear. They don't want to make it, too complicated. It's almost always linear. I can't recall a single time where it wasn't linear. So hopefully you understand what I'm saying. So at 29.6, you would expect it to be at 460. A little tough. Yeah, usually they don't even have this option. Here they not only do you need to recognize that it's going to be above 29%, you need to recognize that it's probably going to be closer to 29.3 rather than 29.6. 15. Is the statement the monthly average cover of low clouds is more directly correlated to the cosmic ray flux than the monthly average cover of high clouds, consistent with figures 1 and 3? Okay. What is the statement? The monthly average cover of low clouds is more directly correlated with the cosmic ray flux than the monthly average of high clouds. Okay, so hopefully you know what this word correlated means. It means they go together, they impact each other. And here, so they ask you to look at figure 1 and figure 3. We have those two right here. And yeah, this is exactly what I was talking about earlier, right? Yeah, this question, I definitely anticipated this one. Yeah, absolutely, it fits. So in the passage and in the table, they say that the cosmic ray flux is affected by the low clouds. And the data here shows that very clearly. Yeah, the graph of the low clouds matches the RCRF very, very closely, whereas like the high clouds versus RCRF, it's like I don't see the correlation. This is just like not related. Sometimes the RCRF goes up when the high cloud cover goes down. Doesn't make sense. Whereas like this one, they go down together, they go up together, they go down together, they go back up together. It's very, very nice. Very compelling data here in figure 3. Okay. Definitely we're looking for yes, right? Because the plot for the monthly average cover of low clouds more closely parallels the plot of RCRF. I don't know how I feel about this word parallel, but I kind of see what they're saying. I think A is the correct answer. B, yes, the low clouds correlate better because the plot of the monthly average cover of high clouds is more closely parallels. No, that's just wrong. C, no, because the plot of the monthly average cover of low clouds is more closely parallels the plot for RCRF. And definitely, yeah, if you ever run into these questions, definitely in a lot of situations you may not understand exactly what they're asking for, right? Yeah, definitely don't be afraid to read the answer choices. Yeah, definitely the reasoning that they provide will kind of guide you in the correct direction, right? Yeah, so hopefully, even if you don't know whether the answer is yes or no, if you read the answer choices, they're like begging you to go check, right? Does the RCRF match the low clouds, or does the RCRF match the high clouds, right? And then once you do that, you can eliminate B and D, and then here you just do it as like yes. That the fact that the graph matches means that the data that they were talking about makes sense. 16. Which of the following figures best represents the monthly average cover of high, middle, and low clouds in January 1992? Okay, so here I'm definitely taking notes, right? Definitely, this is one of those questions where if you're working on paper, it becomes a lot easier. But just take notes anyway. It's not too bad in the digital version, like on a PDF. So we're looking for January 92. January 92. 92 is over here. Cloud cover. So this one looks like 15.4 to me. Or, no, sorry, 13.4 to me. Maybe 13.3. Let's go with 13.3. 13.3 for, what is this? High clouds. And then this is January 1982. This is the middle clouds. Middle clouds are at like 20.2. That's a lot. I don't know. Is that a lot? I don't really know. I don't really do like cloud statistics. And then January 2 for the low clouds. January 2nd over here. What is this? It's like 28.2. Interesting. Something like this. Yeah, so definitely what they want you to recognize here is that high clouds is definitely the lowest. And then low clouds are definitely the highest, right? So it has to be G. Has to be G. Very straightforward, right? Yeah, 1992, find the data, write it down. Yeah, the pattern is that we start low and then go high. High is low, low is high. However you want to say it, right? Just get the correct answer. 17. How clouds are composed primarily of ice crystals, whereas low clouds are composed primarily of water droplets. The difference is most likely because the average air temperature at altitudes from what? Did they talk about this? I don't think they talked about this at all. So here they just want you to like think about it. So clouds way high up in the air are ice crystals. The low clouds are water droplets. Why? Probably because it's very cold at high altitudes. 0 kilometers to 3.2 kilometers is at or below. No. At or below, no. We're looking for above. Hopefully you guys know that 0 degrees is freezing, right? Yeah, so above 0 degrees, water is water, like liquid. but under 0 degrees, water will freeze and turn to ice. Hmm. What's the difference between C and D? The difference between C and D is the kilometer stuff. I think it's going to be D, but I definitely should double check, right? Yeah, so we're talking about high clouds versus low clouds. I'm pretty sure high clouds start at 6 kilometers. High clouds start at 6 kilometers, exactly. It's right here. It's right here. I feel like that was pretty simple. 13.5. This one's definitely H. This one's definitely A, right? 16 is definitely G. This one should be D. I just can't imagine that any of these questions are wrong. I'm like, I don't know. It is possible that I'm just like not reading it properly. That would be really unfortunate. BH, AGD. Very nice. Like, I feel like it's pretty straightforward, right? No need to overcomplicate things. So, like, they tell you about this stuff, and, like, definitely I think the biggest hurdle that most kids need to get over is, like, it's okay if you've never heard of this stuff before. Hopefully you realize, like, what is the, like, if you have, like, 10,000 high school students, how many of them have heard of relative cosmic ray flux? Maybe, like, two. Like, like, obviously, like, if you have 10,000 high school kids, like, two of them are going to be, like, really weird, right? And they just know everything. But I would say, like, the vast majority, like, over 99.9% of kids will have never heard of RCRF. I have never heard of this either. Just if they tell you what it is, pay attention. Yeah, understand that we're monitoring clouds near the ground, clouds kind of in the middle, and then clouds way high up in the air. And then here's the data. And then, honestly, it doesn't even matter what they're talking about, right? Really, the important part for the ACT science test is you see this. We have some numbers. The numbers on the right go up. The numbers on the left also go up. And here, they also want you to recognize it's linear. Yeah. And then here, yes, this graph 3, figure 3, sorry. Figure 3 is the one that matches. That's also very, very important. And then, occasionally they'll just tell you, oh, go find some numbers on, I don't know, 1987 or 1992. Like, definitely be able to do that, right? And definitely, this is very, very important. It was pretty easy this time, but sometimes it gets like really, really complicated. Yeah, the ACT loves this style of graph where they have the time on the x-axis and then they double up on the y-axis, and you just have to pay attention, right? So the dotted lines, the monthly average cloud cover goes with the left side, and then the RCRF, it goes with the right side. And then definitely the RCRF is like a very strange way of measuring things, but honestly, they didn't even talk about that. That didn't even come up in the test, thankfully. That was nice of them. Yeah, definitely. If they said anything about, like, can you describe, like, the importance of 1965 in RCRF? Yeah, definitely everyone's missing that question, right? I mean, not me, but teenagers are all missing that question for sure. And thankfully, like, definitely the ACT's hard, but you have to realize, like, there's like a hard cap for how hard the questions can be, because, like, if you just like take it one step further, right? You start like asking kids about, like, why is it relative? No one's gonna be able to explain that. And definitely, even in the ACT, like, if no one can answer a problem, it becomes an issue, right? You need at least some high school kids to be able to solve it. And then, I think that's the correct mentality. I think you should know for a fact, right? This is just a fact. No matter how hard the questions get in the ACT, some high school student is able to solve it. Like, make it you, right? Let's go ahead and jump back into the 2020 test. Yeah, so yesterday you guys did the first passage, right? It was about the acorns and the squirrels, and not too bad. Definitely you guys did really well. Today you're going to look at the next one. Let's see. Is there anything worth talking about here? Yeah, you're looking for page 41 of 55. This is the passage 2, right? So here we have a periodic substance. Yeah, we have Kelvin. Yeah, we have a lot of information here, right? We have atomic mass, density, specific heat, thermal conductivity. you definitely, like, they tell you what each of this stuff means, right? Yeah, specific heat, thermal conductivity, blah, 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 blah. But honestly, you don't even need to know what it means. You just need to know that, like, there is data for specific heat, here are the numbers. Here's the data for thermal conductivity, here are the numbers, right? Occasionally, they might ask you to, like, interpret some of the data. If they ask you to do that, just make sure you go over here, right? They literally tell you what specific heat is. The units, yeah, they have the units. Sometimes this stuff is important, sometimes it's not important. And then we have figure 1 over here. Yeah, so here, table 1, figure 1, definitely this type of thing, absolutely essential. I don't want to give away all the answers, right? Definitely I want to give you guys a shot to try it yourself. Let's put 6 minutes on the clock. Yeah, definitely I would number your paper 8 through 13, right? Many of you, like, didn't finish the questions yesterday. You, like, save those 10 seconds, write these numbers down before we begin. Alright. 6 minutes on the clock. Questions 8 through 13. 6 questions. Paper, pencil ready. PDF open. You're looking at page 41, passage 2. Let me type that in as well. Yes, this is the December 2020 ACT Science Test questions 8 through 13. If you're all set, can I get a ready in the chat? Alright, I'll give you a 2-minute warning. Let's begin.
I'm super shy, but wait a minute while I make you mine. 떨리는 지금도 you're on my mind all the time. I wanna tell you, but I'm super shy. I'm super shy, but wait a minute while I make you mine. 떨리는 지금도 you're on my mind all the time. I wanna tell you, but I'm super shy. And I wanna go out with you. Where you wanna go? Find a little spot, just sit and talk, looking pretty. Follow me. 우리 둘이 나란히 보이지? 내 눈이 갑자기 빛나지? When you say I'm a dream. You don't even know my name, do you? You don't even know my name, do you? 누구보다도 I'm super shy, but wait a minute while I make you mine. 떨리는 지금도 you're on my mind all the time. I wanna tell you, but I'm super shy. I'm super shy, but wait a minute while I make you mine. 떨리는 지금도 you're on my mind all the time. I wanna tell you, but I'm super shy. 나 원래 말도 잘하고 그런데 왜 이런지 I don't like that. Something out about you, yeah, you're special and you know it, you're the top, babe. I'm super shy, but wait a minute while I make you mine. 떨리는 지금도 you're on my mind all the time. I wanna tell you, but I'm super shy. I'm super shy, but wait a minute while I make you mine. 떨리는 지금도 you're on my mind all the time. I wanna tell you, but I'm super shy. You don't even know my name, do you? You don't even know my
right, 6 minutes is up. Yeah, if you're not finished, yeah, take your guess, right? Yeah, if you need to blindly pick an answer, go ahead and do that. If you can eliminate even one answer choice, that's a good place to be. No questions blink, no questions blink. Let's mark your results. Starting from 8, we have G, 9 is A, 10 H, 11 is C cat, 12 is J, 13 is A. Yeah, definitely, yeah, you want like a 4 out of 6 correct here. You know, like 4 out of 6, not a bad place to be. Obviously, you want to do better than that. If you're looking for like a top score, again, yeah, really you need to start getting all 6 questions correct, especially in the first couple of passages. If you got questions wrong, it's okay, right? Yeah, that's why we're here. We're going to practice it together. Let me know which ones you missed. Let's talk about it. 13. What is the meaning of the value of density of indium given in table 1? Okay, so in table 1, indium density is 7.31. So 7.31, so here it means like at 298 degrees Kelvin. I think that's like 25 degrees Celsius or so. 298 Kelvin to Celsius. Yeah, so what is this? This is like what? 77 degrees. I'm so good, bro. I'm so good. Okay, so at 77 degrees Fahrenheit, this is like, you know, a little hot. It's like room temperature-ish. It means that 1 gram of this stuff, or no, it means that 1 cubic centimeter, what is 1 cubic centimeter? Like, it's like a sugar cube, 1 mil. 1 cubic centimeter of indium is going to weigh 7.31 grams at 77 degrees. Right? So each cubic centimeter of indium has a mass of this. I don't know what else to say. Does that make sense? Like, what's the confusion here? Maybe you just ran out of time. Like, this is density. Yeah, each cubic centimeter of indium has a certain mass. Yeah, like, I mean, yeah, definitely, like, when you're, like, well, you have, like, 10 seconds, right? Like, it's hard to, like, get the words in the correct order, but choice A is the one where the words are in the correct order. Yeah, question 9. According to table 1, at 298 Kelvin, the specific heat of indium is closest to the value of the specific heat of which of the following elements? Okay. Okay, so we're looking for indium, table 1, specific heat. Okay, so we're looking for indium, specific heat is 0.223, and they're saying like one of these 4 is going to be super close. It's probably barium, right? Barium looks pretty close. But none of the other ones are even close. It has to be barium. Yeah, it has to be barium, right? Just here. Yeah, again, table 1, indium, specific heat, which one's the closest? Yeah, so indium is at 0.223. Yeah, the only one that comes even close is barium at 0.204. Yeah, definitely you could like, if I'm actually taking the test right, I'm taking notes here. This is where I'm taking notes, right? So I'm writing down like, BACASRTL, and then yeah, definitely I'm right. Yeah, I'm making note of this one, right? This is the important one. 0.233. Barium is pretty close. Calcium is not super close. Strontium is close, but definitely barium is closer. And then we have thallium. This one's not close. Yeah. You make sure you're looking at the correct column, right? This type of thing. Like, you know, so many kids are like, oh, I was looking at this column. Well, don't do that. They told you to look at specific heat. That's kind of like the point of this test. Question 10. Based on the definition of thermal conductivity and on table 1, does strontium or thallium conduct heat more effectively? Okay, so this one's a little bit more complicated, right? So we're comparing strontium to thallium, and we're looking at thermal conductivity. So we have strontium SR and thallium TL, and we're looking at thermal conductivity. So strontium, okay, they're both really, really high. So we have 35 and 46. So here, I just know that thallium is going to be the correct answer. But here, if you don't know, it's the ability. What is thermal conductivity? It is the ability to conduct heat. The greater the thermal conductivity, the more effectively the substance conducts heat. So like, what's going to have, like aluminum, right? Yeah, so here, hopefully this makes sense. Aluminum absorbs heat ridiculously quickly, right? Yeah, so if you like have a can of soda or an empty can of soda, right? You hold that empty can of soda for like 10 seconds. It's going to start heating up instantly, right? Yeah, that's because the thermal conductivity is very, very high. It absorbs and transfers heat. So anything that absorbs heat quickly, it also like dissipates heat very quickly as well. As far as I know, I think that's true. I think that's a relatively safe statement. If something absorbs heat quickly, it also dissipates heat quickly. I don't know any exceptions to that rule. There might be something, I'm not sure. But in general, most people think about thermal conductivity this way. It works both ways. So here, since the thallium has a higher thermal conductivity, and they tell you it's the ability to conduct heat, it conducts heat faster. So definitely the thallium. So hopefully you were able to eliminate F and G and J, right? You can eliminate G and J because the thermal conductivity is not less. It's wait a minute. So you should eliminate F and J. Yeah, the way that they order the words is a little bit confusing. But here, yeah, hopefully you can tell like thallium has the higher thermal conductivity, and they even tell you that the thermal conductivity is the ability to conduct heat. The greater the number, the more effective the substance conducts heat. And the question is specifically asking like which one conducts more heat. Yeah, definitely it's thallium. Does that make sense? Yeah, like this type of skill, like this is like the perfect example of a question in the ACT science test. This is the type of stuff that they want you to be able to do. You read the passage, look at the table, get the correct numbers, put all the information together, right? And then understand what they're telling you in the answer choices. That's probably the hardest part. 10 is each. Make sense? Yeah, definitely. I would take notes, right? Yeah, if you missed question 10, if you only missed one, you're a really good spot. Yeah, definitely write it down, right? Take a look at it again some other day. Yeah, work through this set again. Yeah, hopefully like on Saturday, right? A really great thing to do would be just work through this whole test again. Make sure you're nailing all the questions. And then once you're feeling really confident about this one, yeah, hopefully you guys still have the link for all the tests, right? Then you just pick one. Pick another one. Try that one. Okay. Yeah, so I finished my coffee. I did some jumping jacks. I think I can do it. I think I can do a set. Yeah, so hopefully you guys have noticed I give you an extra 15 seconds, right? Yeah, you have to move even faster in the real test. But like using the PDF, like doing one passage at a time, it can be kind of a hassle. So I give you an extra 15 seconds. So we have 18, 19, 18 to 23. Oh, I looked up their names. Yeah, the half Australian girl, her name's Danielle. Yeah, of course I don't remember the American name. Yeah, I remember all the Korean names, but I can't remember the, the American name. That's funny. I guess her name's Australian. I'm being very America-centric right now. It's okay. It's okay. It's fine. Okay. I'm like delaying. It's because I'm nervous. Okay. Oh god, you have to move so quickly, and definitely the questions actually start getting hard. Yeah, definitely. Like once I get to like passage 5, passage 6, like I'm hoping that I have time left over, right? But for when I'm demonstrating it in these classes, I want to be able to get them all correct, even in the time limit. But generally speaking, the first couple passages, I'm flying through these. I have like 10 extra minutes at the end. But definitely I want to be at a place where like even if I have to do the hardest questions in 5:45, I want to be able to nail it every single time, right? So we have 1, 2, 3, 4, 5, 6 questions. 5:45. Let's begin. So we have acid-base titration is the technique in which precise volumes of a titrant and acid or base solution are added incrementally to a known volume of a sample solution and acid or base solution respectively. This process can be monitored by adding an acid-base indicator, a substance that changes color over a certain pH range. The sample solution by measuring the solution's conductivity. Conductivity is measured in kilosiemens per centimeter. Ks over cm is a measure of the substance's ability to conduct electricity. 2 titration experiments are done at 25 degrees Celsius using a 0.1 molar sodium hydroxide solution, or either a 0.001 molar hydrochloric acid solution, or a 0.001 molar acetic acid solution, where m is moles of acid or base per liter of solution. All solutions were aqueous. The acid-base indicator solution nitrazine yellow was used. Nitrazine yellow is yellow for pH less than 6, or blue if the pH is greater than 7. Okay, so we have some experiments here. A drop of nitrazine yellow solution was added to the flask containing 100 mL of HCl solution. A probe that measures the conductivity was placed in the solution. Then HCl solution was slowly added to a HCl solution in small increments. After each addition, the HCl solution was stirred, and the solution's color and conductivity were recorded. Okay. Yeah, so it's yellow, 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 blue, blue, blue. Conductivity goes down and then it goes up. Okay, so I think conductivity probably is high if it's acidic. It's also high if it's basic. That's what I'm thinking. Experiment 1 was repeated, except the acidic solution was used instead of the HCl solution. So here, yeah, I think acidic solution is like a buffer, so that's why like you see a different pattern over here. But after a certain point, you start becoming basic, I think. 18, experiment 1, the solution. Experiment 1, that's here. Sample solution was yellow. At which of the following values of the volume of the titrant added? So volume of the titrant added is down here, right? Yellow is these dots. You have blue over here, yellow over here. So we're looking for like 0.5 or anywhere below 1, honestly. It's F. 19, the experiment 2. The sample solution was neutral at which of the following values for the volume of titrant added? Neutral. Probably 1. How did I know that? So here, yeah, definitely for acid and base, you need to know that low pH is acidic, high pH is basic, right? 7 is water, 7 is neutral. Yeah, so here, the transition from yellow to blue occurs right here. So here, you can tell that at this point it's neutral. Yeah, so here it's acidic, here it's basic. Definitely you need to know that. And we'll talk about that a little bit more. In experiment 1, if 2.3 mils of titrant had been added to the sample solution, the conductivity would most likely have been what? Okay, so in experiment 1, 2.3. So 2 is over here, right? So 2.3 would be like here. So it'd probably be like 4.5 or so. Yeah, greater than 3.8. Yeah, you don't even need to know the exact answer, right? You just need to know that it's going to be high. And this is Ks per cm, right? Yes, exactly. 21. Experiment 2. Which solution was the titrant and which solution was the sample solution? Sample solution was acetic acid. The titrant, what was the titrant? I don't even know. Don't even know. Do they say? Where's the titrant? I'm going to skip that one for now. I mean, I guess the answer has to be C, actually, because like none of the other ones are even mention acetic acid. Is it possible that the acetic acid is the titrant? I don't think so. Experiments 1 and 2, the probe that was placed in the sample solution most likely did which of the following? The probe? It measures the conductivity. Cooled the solution, heated the solution, detected the concentration of nitrate yellow. Probably J. It measures the current, the conductivity. So to measure the conductivity of something, you probably want to like conduct something. So the only sensible answer in my mind is J here. A chemist claimed that the experiment 2, pH of the sample solution was greater than the value of the 0.2 mils of titrant added than at the value of 1.8 of the titrant added. Do the results of experiment 2 support this claim? No. That's like a very strange thing to say. Like as we add more, it gets more basic. basic? Yeah, blue is basic. Yeah, it gets more basic. What are you saying, bro? No. Answer is no. The value of the sample solution was yellow. Yeah, it's just A. It's just A. Yeah, it's blue when it's basic. Yeah, high pH means that it's basic. Yeah, that's very important here, right? You need to understand low pH is acidic, high pH is basic. No. You're just wrong. Yeah, the description for B is wrong. Yeah, the answer is correct, but the description, the explanation is wrong here. I feel like this one is also pretty straightforward. I feel like this one is also pretty straightforward. I say that, and then I'm going to miss one, right? FBJCJA. Let's keep it going. Let's keep it going. Yeah, you know, so like a quick like rundown of pH, right? Yeah, pH chart. Examples. Yeah, so definitely you kind of want a sense of like what the pHs mean. So yeah, like water 7. Water 7, water is neutral. Milk is slightly acidic, apparently. I didn't know that. Coffee is kind of acidic. Yeah, like, you know, orange juice, coffee, it's bad for your teeth. Why? Because it's acidic. Yeah, like fruit juice, yeah, lemon juice, super acidic. Yeah, obviously stomach acid is very acidic. Yeah, once you reach like 1 or 0, yeah, this is not a good place to be. Yeah, like two yeah, vinegar. Obviously, if you like put your hand in a jar of vinegar and like leave it there for hours, you're gonna have serious problems. But you know, for a little while, it's fine. If you spill some vinegar on your skin, you just brush it off, wash your hands, you're good to go. Even lemon juice is kind of okay, right? Yeah, definitely if you get lemon juice on a cut, right, it starts burning like crazy. It's because it's super acidic. If you get battery acid on your skin, yeah, definitely like you probably need to go to the hospital. Don't do that. And then basic, yeah, baking soda, milk of magnesia, again, these are fine. Yeah, like 9, 8, 11 even. Like you can get it on your skin, just wash it off. Soap. Yeah, like obviously, like if you just leave soapy water on your skin for like hours, like you like, I don't know, you like soap up your hand and you don't rinse it off, like it's gonna cause severe burns on your skin after like 2 hours. Obviously bleach, like definitely if you get bleach on your skin, you wash it off quickly, it'll be fine. It might be irritated for a little bit, but definitely once you hit like 14, yeah, if you touch this stuff, yeah, you're probably going to the hospital as well. Yeah, definitely like I think actually like ingesting basic stuff is actually much more dangerous than ingesting acid. Yeah, you can drink lemon juice, you're fine, right? Well, it's mostly because your stomach is already acidic, whereas like, you know, like if like this is why the Tide Pod challenge is such a disaster. Yet like your body cannot handle basic materials, it starts freaking out, and like definitely like, if you do the Tide Pod challenge, you're gonna have irreversible damage to all of your organs. Don't do that. It's not worth it. Yeah, especially because like the Tide Pods are like concentrated bleach. It's not even regular bleach. It's like ultra concentrated bleach. It's definitely closer to 14 than 13, I think. Yeah, at this point, like, yeah, you're permanently disabled. Enjoy being a vegetable in a wheelchair. Any questions? Yeah, so here, like, yeah, definitely something weird is happening here. Thankfully, they don't even ask about that, right? Yeah, honestly, like, if it's too complicated, I wouldn't even worry about it. And definitely, this is like, I think, a huge part of just like being successful as an adult, right? Yeah, definitely. I hope you realize that the vast majority of adults, yeah, like, there's huge gaps in their knowledge, right? And how do you deal with that? Most adults, how do you deal with the fact that I have no idea what's going on here? You just ignore it. Like, definitely play to your strengths, right? Yeah, focus on the parts that you do understand. Yeah, so this part's neutral. It's yes, the shape is weird. The reason why this happens is probably because acetic acid is a buffer, an acid buffer. Um, but yeah, definitely all you need to know, it is acidic over here. The thermal conductivity is low for whatever reason. And then, but what's important and the stuff that you do understand, the stuff that I understand, is that yes, it turns neutral right here. That was one of the questions. And then after it turns basic, it behaves just like the sodium hydrochloric acid solution. Yeah, so once you hit this area and it turns basic, then the behavior is normal, just like before. And then for whatever reason, the conductivity is highest when it's either acidic or basic. And that makes sense to me as well. So if it's very acidic or if it's very basic, that means there's a lot of charged ions within the solution. So if you have something that's very neutral, actually, lots of people think that like water conducts electricity, right? Pure water actually doesn't conduct electricity. The water only conducts electricity if it has like ions in it, like if it has like sodium or calcium ions. That's what allows electricity to flow. There's a question for 22. Okay, so they're asking about the probe. So in both the experiments, they used a probe. And here, where did they talk about the probe? Right here. A probe that measures conductivity was placed into the solution. Yeah, so conductivity is the ability of something to carry electricity, right? Carry current. So if you have a device that measures if something carries current and how well it carries current, definitely the most direct way to do that is just like put some electricity through it and see what happens, right? Yeah, so obviously we're not freezing the solution or boiling the solution. That would be ridiculous. That would ruin the experiment immediately. And then like this is also a very strange thing to say, like to detect the concentration of nitrazine yellow. Generally, like an electronic probe is not capable of this type of behavior. Like maybe there are some very sophisticated technologies that I haven't seen yet, but like definitely like maybe like NASA or like the US military has something like this, but like I've never seen anything like this where you can just like put a machine into a liquid and suddenly can tell you like the concentration of the material. Like the more normal way to measure the concentration of stuff is to like take a small sample of whatever you're looking at, and then you have to like titrate things, run some chemical reactions, put something into the solution that like changes color, and then you look at the color, which is exactly what we did here, right? So the way that we're indirectly measuring the concentration of the nitrazine is just by looking at the color. And then you just use like historic data to like kind of get a sense of that. Yeah, J is definitely the only sensible answer in my mind. Yeah, we have a probe that measures the conductivity. Well, how are you going to do that? Well, how about you run some electricity through it and see what happens, right? So definitely that's like a very sensible probe. You put the probe in, it runs some electricity through the solution, and then you have like another probe at the end of the tank, and then you just measure how much electricity ran through the water, right? So if it's very conductive, you're going to see a lot of electrical flow between the circuit. If it's not conductive at all, then you're going to see no electricity flowing through the water. And then like everything in between, you can definitely measure everything in between. Definitely F and G. This stuff absolutely does not make sense. If you're like pouring acid into a cup and then you freeze it, like that's not gonna work. Like then the acid is just gonna sit on top of the ice. If you're boiling it, that's just bad behavior. Like you definitely like OSHA is gonna stop by and like shut you down if you're doing stuff like that. You're like boiling stuff and you're dropping the acids into it. Like that's how you make stuff like mustard gas and fires. Don't do that. Yeah, pretty straightforward, right? Look at the charts. Read what they tell you. This okay. 20. Let's talk about 21. I got it correct, but it was just like I kind of like metagamed the test, right? So the sample solution was I guess maybe this is how they want you to solve it. Like I don't think they told us what the titrant was. They just told us that the sample solution was acetic acid. Okay. Acid-base titration is a technique which uses precise volumes of a titrant and acid-base solution that are added incrementally to a known volume of sample solution, right? So we used acetic acid as the solution, implying sample solution. And then they didn't tell us what was the titration. Oh. Okay, so they're a little vague, but if I read it a little bit more carefully and had a little bit more time, I would have seen it. So the two titration experiments were done at 25 degrees Celsius using sodium hydroxide solution as the titrant. They should have said that. And either a hydrochloric solution or the acetic acid solution as the sample solution. Yeah, I feel like they purposefully made it a little vague here just to make the question harder. That's really unfortunate. Um, yeah, but just from the charts, I could tell that like the sample solution was acetic acid, and definitely like like this is a good example of like where it is helpful if you are like handy with chemistry. Like using the data, I can tell that the sample solution is acetic acid. You don't even need to tell me anything. I just like look at the chart and then the date, like the description, and I already know that. But this part, we used this, but they don't tell us like how we used it. Yeah, so definitely, if we have a titration experiment, one of them is the titrant, and then the other one is the sample solution. Yeah, thankfully, yeah, if they had, what if they had another one where the sample solution was acetic acid? I would have been in a lot of trouble. I guess like if, I guess like even if they had like acetic acid and HCl here, I would have picked C anyway because it doesn't make sense to take an acid and try to titrate it with more acid. Yeah, so definitely, I guess the other way that I could have really known that the titrant was NaOH and not HCl or acetic acid is because as we add more titrant, it becomes more basic. So that's like a really clear indication that we're not adding an acid, we're absolutely adding a base as the titrant. That's a really good way to handle it, actually. Regardless, I was able to get the answer correct. Tough one, tough one. Yeah, this one's almost a little tough. Yeah, this is like very un-ACT. Yeah, usually they just tell you like straight up which one's which, but here they're a little vague about it. Unfortunate. No more questions? Yeah, definitely feel free to ask as many questions as you want, right? Yeah, whatever you want to know, I'll tell you. Okay, oh god. And then I would say like the other big thing that comes into play for this passage 3 is like just common sense. Yeah, there's this question that kids always get wrong in this set. Okay, so what's going on? So there's this Coriolis effect. So like depending on what latitude you're on, because the Earth is spinning, it causes some interesting behaviors. And depending on what latitude you're at, if you like shoot like a disc in a straight line, like straight east or straight west, it like bends. Yeah, and this is caused by the Earth's spin. And they do some experiments on that. And then here there's a question like that asks like, oh, like there's one question where kids really struggle, but this is what you need to realize, right? So here in these experiments, they're doing these experiments at latitude 15, 30, 45, 60, and 75. So you have to realize, right? Like 15 latitude, that's like Ecuador. Like 70 latitude, that's like Greenland, like North Sweden. And like there's one of the answer choices implies that like, oh yeah, we'll like do one experiment here and then we'll do another experiment here and then we're going to come back down here to do the second experiment. Like that's ridiculous. Like if you're going to travel between the latitudes, right, you're going to do all your experiments here and then you're going to go to the next latitude and then you're going to do all the experiments here. It's just absolutely ridiculous, and so many kids pick this answer. It's frustrating. Like there's no way, like even if you have a private jet, why would you do this? It's ridiculous. Like why would you do one experiment at latitude 10, then go to latitude 30, do one experiment over here, and then go back to latitude 10? That's going to take like years, months. Like it's going to take way too long. Nobody enjoys being on the plane, even on a private plane. You show up in Ecuador, you do all your experiments, and then you go to Mexico. Yeah, you don't like go back and forth between Ecuador and Mexico. That's a bad idea. Yeah, it's definitely like sometimes common sense does come into play a little bit. Yeah, it's complicated. Yeah, definitely there's lots of concepts here. Yeah, and I think it's like especially when they introduce all sorts of new concepts, that's when like the common sense starts becoming lost. But you have to like, it's just part of the test. Even when you're like trying to understand all this new material, you have to remember the basic stuff. Like traveling from 15 degrees latitude to 75 degrees latitude, that's going to take like at least 12 hours even on a supersonic jet. Don't do that. Or just only do that once. Don't do that 100 times. How many questions here? 16 to 20. 5 questions. No, it's 14 to, sorry. It's 14 to 20. There's 2 extra questions here. So this time you actually have 7 questions. So you have to move like extra quickly. Good luck. 6 minutes on the clock. Paper, pencil ready. Yeah, definitely number your paper 14 through 20, right? Just save those 10 seconds. Yeah, work quickly, eliminate incorrect answers, use the charts, understand the passage. Can I get a ready in the chat? Brilliant. I'll give you a 2-minute warning. Let's begin.
이 노래는 it's about you baby only you 내가 힘들 때 울 것 같을 때 기운도 이제 나지 않을 때 It's you 날 걱정하니 It's you 날 웃게 하니 말은 해도 돼 But what do you say 멀리든 언제든지 달려와 바쁜 척도 없이 난 나타나 이게 말이 되니 난 물어봐 너는 말야 He's the one that's living in my system baby Oh my god Yes on that I was really hoping that he will come through Oh my god 단 너뿐이야 Asking all the time about what I should do No I can never let him go 너만 생각나 24 넌 행운 아야 정말로 I know 널 알기 전까지는 나 의미 없었어 전부 다 내 맘이 끝이 없는 걸 I know I'm going crazy right 어디서든 몇 번이든 There ain't nothing else that I would hold on to I hear his voice through all the nights 잠시라도 내 손 놓지마 no 걱정 없잖아 Cause I got someone 혼자라도 괜찮아 Cause I love someone 멀리든 언제든지 달려와 바쁜 척도 없이 넌 나타나 이게 말이 되니 난 물어봐 너는 말이야 He's the one that's living in my system baby Oh my god Yes on that I was really hoping that he will come through Oh my god 단 너뿐이야 Asking all the time about what I should do No I can never let him go 너만 생각나 24 넌 행운 아야 정말로 I know 널 알기 전까지는 나 의미 없었어 전부 다 내 맘이 끝이 없는 걸 I know He's living in my system baby I'm going crazy right baby I'm going crazy right baby can't sleep at night. A hopeless romantic all my life, surrounded by couples all the time. I guess I should take it as a sign. I'm feeling lonely. Oh, I wish I find a lover that could help me. Now I'm crying in my room, so skeptical of, but still I wanted more, more, more. I give a second chance to Cupid, but now I'm left here feeling stupid. Oh, the way he makes me feel that love isn't real. Cupid is so dumb. I look for his arrows every day. I guess he got lost or flew away. Waiting around is a waste, and counting the days is November. His loving is good as they say. Now I'm so lonely. Oh, I wish I find a lover that could help me. Now I'm crying in my room, so skeptical of, but still I wanted more, more, more. I give a sick.
All right, 6 minutes is up. Yeah, again, please don't leave any questions blank. Take your best guess. No penalties for incorrect answers. All right, starting from 14, we have H. 15 is B-boy. 16, J. 17, A. 18, J. 19 is C-cat. 20 is F. Yeah, so definitely this one, lots of really strange concepts here. Hopefully, it's good practice, right? Yeah, definitely, you should 100% expect to run into concepts that you don't understand in the science ACT. Yeah, but again, it really just comes down to looking at the charts, analyzing them quickly. Yeah, if they tell you to look at a certain figure, make sure you're looking at that correct figure, right? Some obvious stuff, but this is what you're being asked to do in this test. These are the skills that you're being tested on, right? Any questions here? Question 20. Which of the following statements best summarize the procedures of experiment 3? Right, yeah, so this is kind of the one that I was trying to help you out on. Yeah, so here you can immediately eliminate G and J because you cannot repeatedly adjust the latitude, right? Yeah, like, again, yeah, the difference between 15 degrees latitude and 75 degrees latitude, this is the difference between like Iceland and Ecuador. You can't just like adjust your location. Like that's ridiculous. So you can immediately get it down to the 50-50. You know, we're repeatedly adjusting the disk's launch speed, right? So the question becomes, is the MOD 2 centimeters or is it 200 centimeters? Here, even without reading the material, I'm gonna go with F, because like there's no way that like yes, there's a Coriolis effect, right? But there's no way that the disk is being moved 2 meters. That just sounds unreasonable, like, to me. I mean, it is, I suppose it is possible if you're shooting like a disk on like an actually frictionless surface and it's going to travel like 2 kilometers, then maybe it'll be adjusted by 2 meters, but that's such an unrealistic experiment. The answer has to be F here. Yeah. And then, yeah, how do I know that for sure, right? Well, yeah, so yeah, the 200 meters is the length of the what is this? The length of the, what do they call it? The track. They call it a frictionless horizontal plane, whatever. Well, hopefully, like even just using the diagram, right? Yeah, the deflection is absolutely not 200 meters. It's just is no. Or I guess this is 200 meters. That's quite a bit longer than 200 centimeters. It definitely like so here maybe you were thinking, oh, there's a number 200 here, right? But no, this is definitely wrong. Yeah, this refers to the length of the path, and also this is meters, not centimeters. Um, the MOD, we're looking for 2 centimeters of MODY because each of the discs are 4 centimeters in diameter, right? Hopefully you can visualize this. So if you have 2 discs that are 4 centimeters in diameter, right? So here, this is 4, this is 4. So if this one goes down by 2, now it's here, right? If this one goes up by 2, now it's over here. Yeah, these miss. That's what we're looking for. We're sliding these discs at a certain speed until they miss. And for them to miss, they need to move, one needs to move down by 2, and the other one needs to move up by 2 centimeters. Does that make sense? Yeah, and then absolutely, just, oh, whoops. Wrong button. Yeah, and then absolutely the other like really important thing to recognize is like we're not repeatedly adjusting the latitude. This is a crazy thing to say. Yeah, so again, yeah, like 15's down here. Yeah, how are you going to adjust that? Like, yeah, like are you, yeah, like you're getting on your teleporter? We don't have that. Yeah, even on a private jet, you're not repeatedly going back and forth. You're definitely like, if you took a jet and started like flying back and forth between Ecuador and Greenland, like someone's gonna notice, like they're gonna stop you. Like either the US military or like NATO or Russia they're gonna prevent you from doing that. And then there was another question. 18. Based on the results of experiment 2, by how many millimeters did the ball's MOD decrease when the launch speed was increased from 15 to 20 meters per second? Okay, so we're looking at experiment 2, that's right here. They're asking about 15 versus 20. So the other important thing here is that the units of the table is centimeters. Hopefully, yeah, so here you need to know how to convert centimeters and millimeters. There's 10 millimeters per centimeter. So here, let's just do the math. So what's the difference, right? So you do 3.44 minus 2.58. It's like about, I don't know. Let's just actually do the math. So this one becomes 6, this is 3, this one becomes 8. Yeah, 0.8. It's definitely this. Yeah, so here you need to recognize that 0.86 centimeters is exactly 8.6 millimeters. Yeah, so 1 centimeter is 10 millimeters. Yeah, so 0.8 centimeters would be exactly 8 millimeters. 0.86 centimeters is going to be exactly 8.6 millimeters. Does that make sense? Yeah, I feel like this one's very straightforward. Maybe the only interesting thing here, you definitely have to pay attention to this type of stuff, right? If the ACT like italicizes something, they underline something, right? It means that it's essential for the problem. Yeah. If you ignore things that are italicized, you're absolutely missing the question. Please absolutely pay attention to this stuff. 17. Yeah, one more time, right? Yeah, so we're looking at experiment 2. That's here. You know, they're asking you to look at 15 versus 20. How much did the MOD change or decrease? You know, you do the math. You get 0.86. Then you need to recognize that 0.86 centimeters is 8.6 millimeters. And then 17. The study made certain use of the same ball in both experiments 1 and 2. The students most likely did this to ensure that the ball's MOD would be A. Yeah, I guess this one's a really great one to go over, right? Yeah, so here's like a really obvious example. Maybe you're measuring like how fast your kid is growing, or maybe you're measuring how fast some person in your class is growing over like 2 years, right? So if you're measuring how quickly somebody is growing over a period of 2 years, you want to make sure you're measuring the same person, right? If you are measuring one person for the first year, and then you're like, oh, that guy's busy, let's just measure somebody else. Like, you have to realize, like, this ruins the point of the experiment, right? Like, you're no longer measuring the increase in height of this individual. Like, the experiment has failed. So here, like when you're measuring like MOD, you want to make sure that your data is consistent. So like obviously, if you have one ball, like let's say you're doing an experiment with a tennis ball, and then suddenly you start, you're just like for whatever reason you lose the tennis ball, and so you will get a bowling ball. Like this is not going to work. Like the experiment is not consistent. Like you just need to start a new experiment, or like find that tennis ball, or like maybe the best thing you can do is like find a similar tennis ball, one that's like identical, same brand, same like dimensions and weight. Am I making sense here? Yeah, so, and another way to say that would be to make sure that the experiment, the MOD, is unaffected by the variations in the object's shape or mass. Yeah, like, this one you absolutely need to understand. Obviously, like, if the data was the same for each trial, that's like, I would say that's not a particularly useful experiment. I suppose, like, there are certain experiments where if you get the same result for every single situation, that is an interesting result. But that's relatively rare. That's absolutely not what's happening in this experiment. Different for each trial. I mean, it's not that the ball is causing the data to be different. It's the speed and the latitude that's causing the data to be different, right? Yeah, absolutely, D is incorrect. And then yeah, B doesn't make sense. Like, this is the whole point of the experiment. The variations in launch speed and latitude affect MOD. That's the whole point of the experiment. Yeah, it's just as simple as like, yeah, like, you know, let's say like you want to know how much weight you'll lose if you eat salad for every meal, right? But like, you know, you run out of salad, so you have McDonald's. Well, you know, the experiment failed. It just doesn't make sense. Yeah. So it would be a similar situation here, right? It would be like, yeah, you're using a tennis ball for these experiments. You lose the tennis ball. Oh, whatever. We'll just use a bowling ball instead. No, that's just bad science. That's just doesn't make any sense. It's wrong. That's why we're using the same ball. Very straightforward, right? Yeah, excellent question. Like, this is the type of stuff we need to go over, right? Because, you know, once like, there's a lot of questions in the ACT, all the sections, honestly, where you like once you see the answer, it's just so obvious, right? You definitely don't miss this type of question moving forward. Okay, yeah, we'll just keep going to the harder and harder questions, right? Let's see. What do you guys think? Do you guys want me to do it in under 6 minutes still, or do you guys want to take it slow this time? It basically comes down to like, do you want me to be stressed out or no? It's okay. It's okay for me to be stressed out. Here we have passage fun. Take it slow. Yeah, definitely. I feel like, definitely. It is nice to see how to do it in the time limit, but definitely, if I have more time to explain it, I feel like that is pretty valuable as well. Okay, let's take it a little slow here. I appreciate that. Definitely. You know, being stressed out is sometimes, you know, I'm only being stressed out for like 5 minutes, right? It's not that bad, but like, definitely if you're in a situation where you're just like stressed out 24 hours a day, like that's unhealthy, right? That you're at that point you're like shaving years off your life. Your hair's gonna gray, your health is gonna deteriorate. But you know, being stressed 5 minutes at a time, honestly, that might even be healthy. Okay. 1, 2, 3, 4, 5, 6, 7 questions here. Passage 5 from the 2014-2015 test. An astronomy class is given the following facts about stellar evolution. So the evolution of stars sounds cool. A star's evolution can be divided into 3 stages: pre-main sequence, pre-MS, main sequence, MS, and post-main sequence, post-MS. 2. Gravity causes part of a cloud of gas and dust to collapse and heat up, creating pre-MS star. The star's hot dust and gas emit its energy. Okay, well, that makes sense. 3. A pre-MS star becomes an MS star when the star produces the majority of its energy by fusing hydrogen nuclei, protons, at the center to make helium nuclei. You know, that also makes sense. Yeah, this is how stars work, right? So definitely the gas in space are attracted to each other because of gravity. And then what does it mean to be a star, right? It means that you have so much hydrogen, like an unfathomable amount of hydrogen, right? Yeah, like the sun is what, like 1,000,000 times bigger than the Earth or something? Yeah, what's the number? I don't think it's quite 1,000,000. I think it's like 100,000. Only 109? What does that mean? Okay, so they're talking about the diameter, but how about in terms of mass? This makes more sense. It's about 333,000 times as big as the Earth. So once you get enough hydrogen gas that you're 333,000 times as big as the Earth, the gravity of that gas becomes so large that the gravitational force. When I like put my hands together, right? Why don't my hands fuse? Well, it's because like my hands are made of atoms. They have electrons, and the electrons repel each other, right? So, if my hands were in a star, if my hands were in a black hole, the electron repulsion is no longer strong enough to keep my hands apart. So it's a similar situation in the sun. So normally hydrogen gas, like they don't fuse because the electrons like repulse each other, right? But once you get to the 333,000 times the size of the sun, the gravitational force within the sun is stronger than the electron repulsion of these atoms. This is what causes the atoms to fuse together. And that's the point where it becomes a star. And the fusion of the hydrogen into helium releases a giant flaming explosion. An MS star becomes a post-MS star when the star expands into a volume and produces the majority of its energy by fusing hydrogen to make helium in a shell surrounding its center. Okay, and then it definitely gets super complicated. The more massive the star, the more rapidly the star through each of the three stages of evolution. If you want, definitely this is one of the coolest things I learned in college, right, in astrophysics. I explained to you the first step of the star, right? You need to get large enough where the hydrogen atoms are being fused together. The electron repulsion of the hydrogen atoms are no longer strong enough to keep them apart, and definitely that causes that's what creates the star. Right now, it's like a huge flaming ball in space. For a lot of stars, once all the hydrogen is turned into helium, then it's done. But you could get stars that are way bigger than the sun. And then, so what happens then is you can get the gravity that's even strong enough to fuse helium together to create carbon, oxygen, and nitrogen, which is crazy. And then, definitely lots of stars stop there as well. But then you can have a star that's even bigger than that, and then it starts fusing the carbon, oxygen, and nitrogen into silicon. And obviously a lot of stars stop there, but you can have an even bigger star where the gravitational force starts fusing the silicon into iron. And then once you have iron, actually it stops working, because once the atoms get to a certain size, so far the reason why you're able to have stars is because when you fuse smaller atoms together, it releases like a giant ball of fire energy. Whereas if you start trying to fuse, it actually takes energy. Like when you fuse iron atoms together, that actually absorbs energy, and that's why once you get to super huge atoms like uranium or plutonium, actually it's the opposite. So it takes energy to create uranium. That's why it releases energy when you break uranium. That's how you create nuclear weapons, right? But definitely, once you get to the iron stage, you can still have stars that are ridiculously huge, where the gravitational force gets to a point where you no longer have atoms. What can happen is if you have neutron stars. What are neutron stars, right? Neutron stars are so massive that, so you have the atom nucleus, and then you have the electrons around the nucleus, right? Well, it gets to a point where even that, the gravitational force is so strong that the electron cloud collapses into the nucleus. That's what creates a neutron star, right? So if you have protons and a neutron, you collapse them together, that creates a neutron. That's why it's a neutron star. And then neutron stars are very cool. Neutron stars are usually spinning at a ridiculous speed, which causes pulsar beams. And then obviously you can have stars that are even bigger than that, and that's when it starts creating black holes. Definitely you can get to a point where the gravity is so strong that not only are you collapsing atoms into itself, you are now bending light back into itself, and once you start bending light into itself, then you start affecting how time works around the field. And definitely black hole physics is too hard. But yeah, definitely really cool. And I think the part that I left out was for most stars that are not strong enough to fuse certain atoms, what happens is they start it gets to a point where they start expanding, and definitely that's what's going to happen to our sun. Most stars, once they start running out of fuel, they just start getting bigger and bigger and bigger, and then they explode. And actually, where does all the stuff in the universe come from, right? Well, it's because certain neutron stars will go supernova, And then certain neutron stars, yes, if you have like a kind of a specific amount of mass, like if certain conditions are correct, they can, for whatever reason, I forget actually why they explode. And so when you explode a neutron star, that's where you get all the unique elements. Yeah, so for most stars, you only have helium, hydrogen, helium, carbon, oxygen, nitrogen, silicon, and iron. But when you explode a neutron star, right? So you have this like super dense mass of just protons and electrons and neutrons all together. And when that explodes, then you get like this random assortment of materials, and that's why like the heavier atoms are so rare. Yeah, and that's how the universe happens. Yeah, MS star becomes a post-MS star when the star expands in volume, produces the majority of its energy by fusing hydrogen to make helium in a shell surrounding its center. Okay. The more massive a star, the more rapidly the star passes through each stage of the 3 stages of its evolution. Yeah, I would say these are the normal stars, right? But obviously, like if you get supermassive stars, yeah, they start fusing the helium, they start fusing the oxygen, they start fusing the silicon. But we're gonna skip all that. It's fine. 2 students discussed the evolution of Angol system. Angol A is a 3.6 solar mass MS star. That means it's 3.6 times as big as the sun. Angol B is a 0.8 solar mass system post-MS star. Angol C is a 1.7 solar mass MS star. 1 solar mass equals the sun's mass. They tell you that. Nice. The 3 stars orbit its mutual center of mass, with Angol A and Angol B much closer to each other and the center of mass than C. What is center mass? I don't like the average of the 3. I don't really understand what they're saying. Student 1. The 3 stars of the Angol system formed at the same time in the same cloud of gas and dust. Angol B, originally the most massive of the 3 stars, became a post-MS star and expanded in its volume, while Angol A remained a MS star because the matter in the outer parts of Angol B are more strongly attached to Angol A than the matter in the interior parts of Angol B. The matter flowed from Angol B to A. Over time, Angol A became the more massive than Angol B. I actually hate these. Yeah, so this is one of those. This is a type of passage that comes up in the ACT, and they like talk about some science stuff, and then they have 2 people try to explain what's going on, and like usually everyone is wrong, and I hate them for it. And they say some really obnoxious things, and it's like really hard for me to keep track of what they're talking about because it doesn't make sense. But I'm going to try my best. So we have another student. Angol B was not a part of the original Angol system, Angol A and Angol C. Angol B and the original Angol system formed different clouds of gas and dust at different times and moved into 2 different but intersecting orbits around the center of the galaxy. During a particular orbit, Angol B encountered the original Angol system at the intersection of the 2 orbits and became a part of the Angol system. Angol B became a post-MS star, while Angol A and Angol C remained MS stars. Angol B never lost mass to Angol A. Angol A was always less massive than Angol A. Okay, so student 1 is saying like Angol B used to be bigger than Angol A, but then Angol A absorbed the mass of Angol B. That does happen. It actually looks super cool. Yeah, like sometimes you get stuff like this. So you have like a star, and then here's a black hole, and then the black hole starts sucking the sun into itself. It's wild. It definitely, like the other thing that's really interesting about stars is that the size and the mass don't really correlate. It definitely, yeah, like neutron stars are very small, but they are like multiple times as massive as a normal star. Like the size of the star is more like the interaction between the mass and the energy that it's releasing. Yeah, so there's like this, the gravity versus the energy. Yeah, if there's a lot of energy, definitely it's really big. If there's too much gravity, though, it doesn't matter how much energy you have. You're very small. And then student B, or student, so and the other important part is Angol A is MS, Angol B is post-MS. So like the natural assumption is that B is older than A, but student 1 is saying like no, they're the same age. It used to be really big, and then the mass. And so the other thing that's very important is that they told you this, right? The larger the star, the faster it transitions, rapidly the star passes through the stages of evolution, right? I mean, definitely, student one's description is possible. Actually, I like this one. Both of these hypotheses actually make sense to me, which is super rare in the ACT. Based on student two's discussion, angle B is part of the present angle system because of which of the following forces exerted by angle B by the original angle system? Well, it has to be gravitational force, right? So here, so they're saying that angle B was just some star hanging out by itself, but the angle B crosses the angle system, and then the gravity forces them to start orbiting each other. Like definitely. It's not magnets. It's not electricity. Nuclear force, no. It's definitely gravity. 25, based on student one's discussion and fact 4 is this one. MS star becomes a post-MS star when the star expands in volume and produces the majority of its energy by fusing hydrogen to make helium in the shell surrounding its center. Probably B. I mean, this is what fits the description, right? So student 1 is saying that the post-MS star expanded in volume while angle A remained a MS star because the matter of the outer parts of angle B was more strongly attracted to A than to the matter in the inner parts of angle B. The matter flowed from B to A. And so B becomes a post-MS star. So this interaction that they're talking about occurs once angle B becomes post-MS. A post-MS star is a star that expands in volume and produces the majority of its energy by fusing hydrogen to make helium in the shell surrounding the center. This is the important part, right? And so the MS star is fusing the hydrogens at the center. The post-MS star is fusing the hydrogen outside the center, in a shell outside of the center. That's what we're looking for, right? B. 26. Suppose that chemical composition is uniform among the stars formed from the same cloud of gas and dust, but the chemical composition varies among the stars formed from different clouds of gas and dust. Student 2 would most likely agree with which of the following statements comparing the chemical compositions of the stars in present-day angle system at the time they formed. It's definitely G. So they're saying, like, pretend or imagine that the chemical composition of a star depends on where they formed. So student 2 is saying that A and C formed at the same place, but B formed somewhere else. Well, that must mean that the compositions of A and C are the most similar. B would be unique, right? Because it was made somewhere else. I think it's as simple as that. 27. The mass of the sun is 2 times 10 to the 30 kilograms. What is the mass of angle C? Angle C is 1.7 solar mass, so we need to do 2 times 1.7. That's going to be 3.4. 3.4, yes, C. 2 times 1.7, 17 plus 17 is 34. Therefore 2 times 1.7 is 3.7, or 3.4, excuse me. 28. Which of the following statements best explains why the reaction described in fact 3 requires a higher temperature and pressure? What are they saying? Which of the following statements best explains why the reaction described in fact 3 requires a higher temperature and pressure? What is fact 3? Pre-MS star becomes an MS star when the star produces the majority of its energy by fusing hydrogen nuclei protons at its center to make helium nuclei. Okay, this is like the normal star part, right? A star is a flaming ball of fire in space because it's fusing hydrogen in the center. This is just a star. Okay. Why does the reaction require a higher temperature and pressure? What do you mean? F. All protons are positively charged and like charged charges attract each other. F is obviously wrong, right? So hopefully you know this, like plus, right? Plus is attracted to minus. Plus repel. Yeah. All protons are positively charged and all charges and like charges repel each other. I mean, this is true, but is it the correct answer? I don't know. All electrons are negatively charged, and it's probably G. Why are we talking about electrons? And here, how do I explain this? They just tell you, they actually just tell you that we're talking about protons. This is probably how you want to solve it, right? So a hydrogen is 1 proton and 1 electron, But like when you're in like a super high energy star environment, like the electron just gets ripped off of the proton. So you're really like no longer thinking about hydrogens like you see on Earth. Yeah, like the hydrogen that you see in a star is just like a proton by itself. Yeah, because once you reach like a super high energy state, like a fire or like something that with like a huge amount of electricity running through it, hopefully you realize like if so yeah, like one thing that's hopefully relatively easy to imagine. So if you have like a power grid, right? You have the you go outside on the like or you see the power lines in your neighborhood, or like on the highway you see the big towering ones, right? Yeah, so tons of electricity, especially with the ones when you're on the highway, right? A ludicrous amount of electricity is running through those wires, right? Enough to like power the town that you live in. So what does that mean? Yeah, that means that the wires are usually made of copper. Almost always they're made of copper. And for the electricity flowing through the copper, that means that the electrons that are normally surrounding the copper atoms, they're no longer attached to the atom. They're just flying across the wire. Like, so it's similar in like the sun. Like the sun is like a high enough energy state where like you have the hydrogen atoms, right? But it's not like on Earth where like the one there's one electron and one proton. Yeah, in a super high energy flaming fusion environment, the electrons are just like flying around everywhere. Yeah, it's just you're just dealing with the proton by itself, and they're kind of trying to tell you that in fact 3, right? Um, we're not talking about electrons. The electrons are not super important, at least in this discussion, in my opinion. 29. Based on fact 5 and student 1's discussion, which of the 3 stars in the angle system, if any, was most likely the first to become an MS star? Angle B. Angle B. Why? So student 1 thinks that angle B was the most massive initially. Yeah, angle B was originally the most massive of the 3 stars, and then it became a post-MS star the fastest, right? Well, it makes sense that if it became a post-MS star the fastest, well, it probably also became an MS star the fastest. And definitely also fact 5 just says the more massive, the more quickly it goes through the stages. So it all just lines up. Angle B became MS first. Because, for it to become post-MS first, well, it probably became MS first as well. And then definitely the fact 5 also is in line with that conclusion. Question 30, based on fact 5, would student 2, agree that by the time angle A stops being an MS star, angle A will have spent as much time being an MS star as angle B spent being an MS star? Angle B is post-MS. What's the question? So once angle A stops being an MS star, will angle A have spent as much time? Probably more, yeah, because so angle A is a star evolution is slower because wait a minute, let's check it one more time. No, angle A is bigger. I mean, I don't want to overcomplicate it. Yeah, definitely. Like this discussion is way oversimplified. Yeah, when the star goes through its various stages, it like has really violent contractions and explosions and expansion periods, and in those periods, stars lose a lot of their mass. But I think here it is like a high school level test, right? So I think they're asking you to assume that angle B in student 2's description is always a 0.8 solar mass post MS star, or always a 0.08 mass. You definitely stars change in mass over time, but I think they don't want you to think about that. I think the assumption here is that angle A was always 3.6 solar mass and angle B was always 0.8 solar mass. So student 2 thinks that angle B is just super old. But since angle A is much heavier than angle B, I think they want us to assume that angle A will have spent less time as a MS star, because larger stars go through the stages faster, right? No. Yeah, I think. Yeah, and like definitely, yeah, and this is where the descriptions become super helpful, right? Because according to student 2, angle A has always been more massive than angle B. Yeah, and I want to go back to one of the questions, make sure I'm getting everything lined up properly. No, okay, this one, I need to fix 29. I actually messed up. Yeah, for some reason I thought angle B was the most massive, but angle B is not the most massive? Wait a minute. Let's think this through. It's because student 1 thought that angle B was most massive initially. Yeah, okay, so I think I had it right before. Yeah, okay. Oh god, yeah, there's lots of things going on in question 29, right? So we have to use student 1's discussion. So student 1 thinks that angle B used to be the most massive, therefore it would have gone through the stages faster. That's why it's B. Okay. Tricky. I'm overthinking it, right? Yeah, my initial analysis was correct. Yeah, I'm overthinking it. Don't overthink it. It's definitely gravity. It's definitely B. That's what they said. So it's while the matter flowed. Well, the matter flowed according to student 1 while B was post-MS. So angle B was doing this. B, that's the description that they have, right? Post-MS fuses hydrogen in this shell. And then 26, I wrote down G. That just makes sense. Yeah, so student 2 thinks that angle B came from some other area. So that probably means that angle A and angle C was made of the same stuff. And then 27, I picked C. This one's just basic math. C is 1.7 times the mass of the sun. So 2 times 1.7 is 3.4. 28, I picked a G. Yeah, I think obviously F is wrong, and I don't think we're talking about electrons here. I think this one's pretty straightforward. And then we just check 29 and 30, right? H, B, G, C, G, E, H. Nice. Tough one. They get harder. They just keep getting harder. Any questions here? Yeah, stars are pretty cool. I like stars. Yeah, like Carl Sagan likes to say, right? We're all made of stardust. And it's just true. Where does the solar system come from? Well, it's because like there was some supernova, and like out of the supernova the sun came to be, and then out of the supernova all the planets came to be, and then now we're here, right? Yeah, after like I don't know, depends on what you believe. Was it like billions of years of evolution? God just showed up one day, like just put us together. That's also nice to think about. Yeah, it is a comforting thought, right? Oof. The next one that you guys are doing is really rough. Godspeed. Let's see. Can I help you guys on this one? Yeah, so this one is molecular biology. I would say, okay, so this, I can definitely help you here. Okay, this one's very confusing for most students. You guys have probably never seen a graph like this before, right? But here we have relative blood CD concentration and dietary consumption of vitamin D, right? Yeah, so your body needs CD. And this is actually very common in biology. The human body, I would say, is very resilient in most, from most perspectives, in my opinion. So here, like the human body definitely makes the most out of what it has, right? And so here, what are they saying, right? So 1 is the normal concentration of CD in the human body. So you almost need like the amount of vitamin D that you need is very, very small. Even if you have like this trace amounts of vitamin D, your body can like take that and be very effective with it. But the issue is that if you have no vitamin D, and this is why it's important to like eat well, because like if you only eat potato chips, you're gonna run into severe issues because you're gonna lack specific nutrients. Yeah, your body is very good at taking very small amounts of nutrients and making it as effective as possible. So here, like, so the FDC recommends that you eat this much, right? But like even if you eat like only 20% of what's recommended, your body's totally fine. And even if you eat like only 2% of what's recommended, your body's still mostly fine. But as soon as you hit 0, your body's running into all sorts of issues. Yeah. That's what they're trying to say. So here, even if you eat the tiniest amount of vitamin D, your body can just start pumping out the CD. But if you eat 0, like you don't have any CD. The body needs vitamin D to make CD. And here's the pathway. So you have vitamin D, it goes into the liver, it's converted into CD. The more CD which is in your system, so how does the body do this, right? Why is it that the CD concentration doesn't go up higher? Well, the body can like actively stop the conversion from vitamin D3 into CD once the body detects that there's a certain level of CD in the bloodstream, right? And then the CD goes into the kidney, the CD is converted into CT, and then as CT causes high levels of Ca2+, and Ca2+ inhibits PTH, which activates. So you need PTH to activate the conversion from CD into CT. But once you have too much CT creates Ca2, and then too much Ca2 causes this to disappear, which would cause, this is how the body knows when to stop making CT. Yeah, so here's another nice graph, right? So here, you have lots of CT, but like once your body hits a certain, so this is very, very important. I would say this is like one of the most important things as far as like your health goes, like the ion concentrations in your blood. Like the body works like, it's one of its top priorities is to make sure that your blood has a proper level of ions. So here, like the body's very finely tuned. So if the body hits the correct amount, it immediately turns off the system. If it's anywhere below the normal amount, it's just like it's firing on all cylinders. We need to make more Ca2+. We need more calcium. We need more calcium. It's just, and then as soon as it hits the correct amount of calcium, the whole system shuts off immediately. It's really nice. Okay. So now we're in page 45 and 55. We're back in the essay, ACT 2020 science questions 21 to 26. All right, we have just enough time. Let's go ahead and get started. 6 minutes on the clock. Paper, pencil ready. You're looking at page 45, passage 4. Work quickly, eliminate incorrect answers. You can definitely go over any questions that you miss. Let's begin.
부시는 껍가루에 눈이 따끔해 눈물이 고여도 꼭 참을래 내 맘 막힌 비밀 쓸어 노릇거울에 넣어두고서 영원히 돼감을 순간이니까 우리 둘의 마지막 페이지를 잘 부탁해 어느 작별이 이보다 완벽할까 Love me all with you spring 꽃이는 날 goodbye 이런 걸 말이 어울려 냥꽃잎 같은 안녕 우리 봄날의 클라이막스 얼마나 기쁜 일이야 Love me all with you spring 봄바람처럼 Love me all with you spring 봄바람처럼 기분이 바라건 노래 부르네 입꼬리는 살짝 올린 채 어쩜 이렇게 하늘은 더 바람은 더 완벽한 건지 오늘따라 내 모습 맘에 들어 정말만 그날처럼 예쁘다고 말해줄래 어느 이별이 이토록 달콤할까 Love resembles misty dream 꽃이는 날 goodbye 이런 걸 말이 어울려 냥꽃잎 같은 안녕 우리 봄날의 클라이막스 얼마나 기쁜 일이야
2 minutes left.
Love resembles misty dream 난 구름처럼 Love resembles misty dream 난 구름처럼 너도 언젠가 널 잊게 될까 지금 표정과 오늘의 향기도 한점 사이에 스쳐간 봄날의 꿈처럼 꽃이는 날 goodbye 내 대답이 날 울려 냥 약속 같은 안녕 우리 봄날의 클라이막스 얼마나 기쁜 일이야 Love me all with you spring 봄바람처럼 Love me all with you spring 봄바람처럼 Love resembles misty dream 난 구름처럼 Love resembles misty dream 난 구름처럼
All right, 6 minutes is up. Yeah, thank you guys, so much for making it to the end of the class. Yeah, hopefully you're seeing some good results. Yeah, let's take a look at the answers here. Very impressive. Yeah, still 10 kids left. And again, I just so appreciate you guys being here. You're taking time out of the summer. Pretty crazy. So we have questions 21 to 26. Correct answers. We have B boy, 22F, 23D dog, 24H, 25A, 26 is J. Yeah, anyone get all 6 questions correct here? I mean, that's the goal, right? Yeah, hopefully, definitely. You want to get to a point, you just it's a good idea to just like keep, yeah, brilliant, absolutely brilliant. Yeah, you want to get to the point, like, you want to practice until you get that feeling, right? Like, you want to know what it feels like to get all the questions correct, right? And you like hold on to that feeling, hold on, like try to remember exactly what you did. Yeah, you just need to replicate that scenario as many times as possible, right? Yeah, yeah, definitely. Like, yeah, until you get to a point where you can nail all 6 questions, like it can be a little like daunting, and like you kind of feel like you're like lost and like trying to find something that isn't there. But like once you see it, once you have it, like then you can like, yeah, just do that, right? And definitely, that's a really good place to be. Really good place to be. Excellent work. Yeah, especially this one's a really tough one. It definitely, I helped you guys out quite a bit, right? I kind of fed you a ton of data here. Any questions? Yeah, definitely feel free to ask any questions. I'm willing to spend some extra time going over the questions. Yeah, but definitely, if you guys got places to be, I definitely understand that. Yeah, thank you so much for being here. Yeah, we'll take a look at the math test together tomorrow. Definitely bring your calculator, right?